Hello, can you hear me?
Yeah, I can.
Can you guys hear me? Okay, cool. Thanks. All right. Yes. Right. So you can see my screen, right? I'm gonna need to do some math. Okay. Okay. Thanks. Okay. Today we'll be looking into storage and indexing, and we need to perform some calculation. So basically, we have one question that has 3 sub questions, and then another question is like it's very simple. Okay. So we have a description of relation, and based on that we have a couple of questions. So we need to understand and read the description very well so that we can answer these questions. And most of the information are given, and some of the information are not given, then we need to make some sort of assumption during that case. Okay, let us read together. Suppose we have a table relation 1, 3 attributes ABC, and AB together is a key. Size of A field is 4 bytes, B field occupies 12 bytes, and C field occupies 8 bytes. Relation 1 contains 100,000 records. Okay, so total 100,000 records you have. Among these 100,000 records, okay, 100 different values for A. So we have in total 100 different values for only A. So on average, we have 100 divided by. Okay, so we have 100,000 divided by 100 will be like one value of A on average will appear. So 1,000 different values for B and 50,000 different values for C. Relation 1 is stored with a primary index on the composite key consisting a pair of attributes A, B. Okay, and so this is the relation. So A has 4 bytes. B has 12 bytes, and this one is 8 bytes. Total we have 100,000. Okay, so the B plus tree has assumed this index has 2 levels, including the root page and excluding the leaf page. So that means if you include the leaf, the B plus tree will be, there will be three level, like root, then intermediate levels, then the leaf nodes, which points like which holds the data directly. So assume that each assume that in this database each page is 4 kilobytes, of which so 4 kilobytes is 4,096 bytes, of which 250 bytes are taken from the header information. Record location within the index use a 4-byte row ID. Assume that reading a page into memory takes 150 milliseconds, and the time that needed for any query can be approximated by the time spent doing disk IO. So we can assume that the time will take the time to perform a query is equivalent to reading a page into memory. Same, the number of pages total needs to be read. Okay, the first question: calculate the space needed for the records per data for relation 1. So based on the description, you need to try to read the description one again, and based on the description, we need to answer this question: how much space required for the records or data for relation 1? This we need to compute the space, and we have some hints. For example, how much space is used by a single record. A single record is 12 byte plus 4 byte plus 8 byte is 24 bytes, right? So single record contains 4 bytes, 24 bytes. And then how many record per page? So each page has 4096 bytes, of which 250 bytes are taken. So 4096 minus 250, calculate, it will be 3086. Then you need to divide total space. So how many record can hold per page? So space in per page and how much a single record occupies. Then you can get the how many record per page. Then you have to calculate how many pages for the entire table. So we have 100,000 record. And then we need to convert this back to space. Note that each record is not split across a page. So either you have like 10 records or 11 records. It cannot be 10 and a half records in a page. And each page has a header. So header each page contains some information. Okay. I will give you, if you have any question, let me know, and I'll give you some time to read and answer this question. Try to compute this answer after 5 minutes, 6 minutes. I will ask you to explain if anyone have the answer, and then we can discuss the solution. If you have any question, you can let me know. Okay, does anyone have any idea what would be the result? This space. Excellent. So 160 record per page and 625 pages in all. Yeah, that's great. Would you like to share how did you calculate? Okay, yep. Thank you. I have a question. Index entry is a combination of A, B. For index entry, we'll in the next tutorial we'll compute. We can see the how to compute the index for the index, how to store the index. Yeah, index entry would be a combination of A, B. Okay, so as Jinghan shared the solution with us. So each page has 4 kilobyte minus 250 bytes, right? So 3,846 bytes available to store records each page, and each record needs 24 bytes. So we can fit in one page 3,846 divided by 24. So it will be 160 records in a page. So it will be 160 point something, right? But we cannot fit half of a record in a page. So the next record would have to go to the next page. So this is why we'll round down to the integer. So we'll take the floor value here. So in the case of number of page divided by record. So remember that in sometime in these computations, sometime we may need to take the floor value when we round an integer, and then sometime we need to take the ceiling value. So it depends on the condition. So for here, in this case, we'll take the we'll round down. So take the floor value. Okay. Since relation 1 has 100,000 records, we need to so total number of one page fits 160. So if we divide it 100,000 divided by 160, it will be 625, right? But I think it should be a fraction. 110 divided by 160. Oh, that's not a fraction. Okay. But if it is 62.5 pages, then we have to write 62. 625 instead of 625, we have to write 626. Okay, so one page is 4 kilobytes. So if we so 4 kilobyte into 625, 625. Sorry. So 4096 multiplied by 625. So it will be approximately 2.5 megabytes if you divide it by 0. Yeah, sorry. 5. All right. Let's move to the next question. Calculate the time taken to perform a table scan, linear scan through table 1. How many pages are needed to make up the space occupied in the table, and how many pages will be read from the disk to a table scan? So if we perform a linear search, how much time would it take to scan the entire table? Any idea? Anyone? So we got 625 pages, right? No, it does. The reading into memory is 150 milliseconds. 625 multiplied by 150 millisecond. Sorry, 625 multiplied by 150 millisecond. So it is approximately 93 seconds, right? So if I divide by 1000, 93.75, so roughly about 1.5 minutes to perform the entire table scan linearly. Okay. Any question? Okay, let's move on to the next question then. Calculate the time taken using primary index to execute the following query. Assume the selectivity range on condition B is about 10%. So as the question says that we have a B plus tree on these two records, right? Okay, and B plus tree has total 1 root, 1 intermediate, and 1 leaf, total 3, right? So if I try to, let's see, can I annotate? Yes. So if this is a B plus tree, and so we have 1 here, and then the rest will go to the leaf nodes. It holds the records. So in order to perform a scan, we need to read this one page, this one, another page, either this one or this one, depending on the value. And then this one will be for this, another page. So total 3 pages we need to read. Okay. All right. Now it says assume selectivity range condition on B is 10%. So the condition here, the B select B, like from where B between this one to this one would be approximately, it will select on the entire select, it will paste on this condition, it will select about 10%. So it will read. So if we have 100 records, it will select only 10 records among them from 100 for only this condition, right? Now we do not have much information about this. You know, we need to make some assumptions when we want to get the results of this. So as I said before, for like first I said we need total 3 pages, right, to read, and 1 page read takes 150 milliseconds. Okay, but before that, how many records are there once we find our value? So we don't know how this how much data will be selected. So it says about B, but for A, how many records will be there for only for A? So we know we have 100,000 records, and if we select A equal to AQG, then out of 100 record, how many value we can get? So it says that there are 100 different values for A. So out of 100 different values, this is one of the values, right? This is one of the values. So this value on average may appear in the database. In the database, so in the database we have 100,000 records, and A equal to appeared how many times? A appeared 100 different values. So 100,000 divided by 100, it will be 10,000, right? Okay. So this will select 10,000 records. Yes, what is the question? Jinghan? $1,000? Oh, sorry. Yeah, 1,000, sorry. Right. 1,000. Okay, so on average, we'll have 1,000 records, right? Will be selected by this condition. This is our estimation. And then we have, for B, it's about 10%. So B will select 10%. So how much it will be? 10% of 1,000 will be approximately 100 records, right? So 100 records we need to. So once we get, so when we traverse the B plus tree and then we arrive at the leaf node, then we can assume that we may have to read 160 records. Sorry, 100 records, right? So 10%, 10 equal to 100. So one page contains 160 records. So we need to read only one page, right? But we may need to read 2 pages if it starts from the middle of the page. If we start reading from the middle of the page, or the data starts from the middle of the page, I assume. So from 1 to 2, let us assume we have to read only 1 page. So for the leaf node, we need to read 1 leaf page, right? And for the B plus tree, so we have 2 index level. So 1 page root, 1 page root, and 1 intermediate node. And then from the leaf, we need just 1 page. We don't need to scan more than 1 page. So we'll have total 3 pages. So 3 pages, that means 1 page takes 150 milliseconds. So if you multiply 3 into 150, it will be 450 milliseconds. Okay. Any questions? $160. So 2 index plus 1 leaf, 1 to 3 pages. So total time would be 3 multiplied by 150, 50 milliseconds. Does anyone have any questions? So let us do the attendance then. We will have 1 question left. Today is week 10. Oh, thank you. Good question. So those who wants to do the attendance, please scan, like you want to mark the attendance with your phone, scan this QR code. I'll go through this link. Okay, Jen How asked one question like, why A equal to 1000 divided by 10? It was not 1000, 10,000 divided by, the question was 10,000 divided by, not here, we're asking this question, right? So 100,000 divided by 100, why it is 1000? Why did he make this one? Yeah, okay. I'll explain again. Okay. So the question asked that how much time it would take if we run this select command, right? Do you understand this part? How much time it will take to, if we run this query? So the total time would depend on how much data we'll get from this, right? Because in here in the question it says assume reading a page into memory takes that the time needed for any query can be approximated by the time spent doing the disk IO. So depending on the amount of data we'll get, we will compute the time. The problem is we don't know how much data we'll get from this query. So therefore, we try to estimate how much data we can get. So in total, we have 100,000 records, but it will not select 100,000 records. It will select a subset of 100,000 record, and we are trying to estimate it. So if we write A equal to AQG, how many data we'll get from 100,000? So from 100,000, there are 100 different values for A, right? 100 different values A. So if we write distinct select from A or something like that, then we can get 100 different values at most. So that means on average, one value appeared how many times? One value of A appeared on average how many times appeared in how many rows? 100,000 divided by 100, right? Does it make sense? Okay. So when A equal to AQG, then we have around 1,000 records approximately. We don't know, but that's our assumption. And then we have another condition, the selectivity range condition on B is equal to 10%. That means for this condition, it selects 10%, whatever we get from the A. That's on average. That's also not approximate, not accurate, like an approximate value. So we get for A, we get 1,000, and for B, we'll get 10% of 1,000, which will be how much? Okay, shall be 100 records. Yep. Yeah, no problem. Yeah, sure. I'll show the QR code again here. Can I send the attendance link? Sure, I can. Here's the link. Let me know when you guys are done with the attendance. Okay. Now we'll see how to create indexes using PostgreSQL. So that means for us, the client will be pgadmin, find which indices already exist for the tables you define in early tutorials and assignments. That's our first task. And then identify an extra index which would be useful for one of your queries you wrote. Supposing that the database become much bigger and many more records in each table, then you can actually see the effect of the index. For a short table, a small table, it will be difficult. I mean, you will be able to see any difference for creating any index. Create this index, the one you need to like extra index, that one you may need in future. Note to check which index are present in your schema plus details, you can use the following SQL command. So go to our pgadmin, run this, and it will show us all the schema that we have in our database. Another way to see this, let's say this is academic stuff. And if you click on the table, you can see the indexes and all the index on it. So academic stuff doesn't have any name. The index should have the index. No, it doesn't have the index. That's primary key. Okay. Flight. No index. Here. Plane. So the primary keys are considered here. The database automatically create an index for each primary key created. Yeah. So anyway, if we want to create an index of our own, how they create that? Any question? So any query for any query. So I have an example. So if give names of authors who born after 1940. If we had to perform this kind of query, we'll create an index like create index name on table and attribute. So this will be the format. So let us create an index for flight. Let's see what we have on flights. Or lecture, let's say. Select start from let's say transcript. Okay, grade F. So if we have a lot of students with F, then we could create some index, something like that. Let's create index grade transcript rate dx on transcript, then rate. We'll try to run something like that. Okay. The index creation is successful. Now we can run the query. Okay. So I forgot to see what was the time initially, but I suppose it will not change because we have only very limited data. So if it's much larger, then it might make a difference. Okay, so good. Any questions? In the next tutorial, we'll be looking at the same question, but the same description. The question will be a bit tricky. Not tricky, similar questions, but it will be mostly based on index probably. Yes, that's correct. And also index create a significant role when you perform the join operation. Then index is much more efficient. No problem. Any other questions? Okay, in exercise 1, why final use of 3 into 150? It's on here, this one or this one, or this one? 1C. Oh, okay. So total time taken using primary index, total time taken using primary index to execute the following query, right? So we will have did you understand that we will have approximately 100 records? Did you get this part? Did you understand? Yeah. So the data is in the database is stored using a primary index B plus tree, and the B plus tree has two. It says B plus tree has 2 levels, right? So you'll read 2 levels. Assume each level has 1 page. Each level has 1 page, and then we'll get from this select approximately 100 records, and 100 record for 100 reading 100 records. We may need to scan 1 page, 1 leaf page. So total 2 levels plus 1 leaf page for 100 records. So total 3. Does it make sense? Linda. Okay. Any other questions? Okay, if you don't have any question, then thank you for attending the tutorial. See you next week. Have a nice weekend. You're welcome. I'm still here. If you have any question, you can still ask me. So tutorial is still, we have a few minutes left.